Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, my plan is the following. We're going to discuss a couple of definitions, one theorem, and we're going to do an example. And the first definition extends the concept of CDF, of cumulative distribution function. Okay, the extension is called a joint distribution function. Okay, the next definition I'm going to show you, the second definition I'm going to show you, generalizes the concept of probability density function. This generalization is called a joint probability density function. Then the theorem that we're going to be discussing, we're not going to provide a proof of the theorem, we're just going to see the statement of the theorem, but that theorem states the two properties that legit joint density functions must satisfy. Okay, and finally, at the end of the video, what we're going to be doing is working on an exercise, doing an example together that is going to help us become familiar with joint density functions. Okay, so that's a plan. Let's begin. So that's our first definition that we're going to be discussing in this video. As you can see, as I advertised, this is just an extension of the concept of cumulative distribution function. Okay, can you see? That is, parallel to that concept. Okay, we're just, instead of dealing with one random variable, we're dealing with two random variables at the same time. Make sense? But the definition of joint distribution function is extremely similar to the definition of a CDF, of a cumulative distribution function. Okay? Okay, next definition. So, it turns out before, right, the PDF would be inside a single integral here, and we would have the same relationship between a CDF and a PDF in the univariate case. Can you see that? So now, instead of having a single integral, we are going to have a double integral. Okay? And but again, the relationship between PDF and CDF, well, that we saw there, is just extended in the bivariate case. So this guy here would be what we call the joint probability density function. Okay? Now let's talk about that theorem. Okay, the theorem that gives you the two properties that a legit joint density function must satisfy. Remember that before, both with probability mass functions in the discrete case and probability density functions in the case of a continuous random variable, right, we had properties that were entirely similar to these, right? Now, instead of evaluating the PDF, we're going to be evaluating the joint density function or joint probability density function, but we are evaluating at a point in the plane, right? But each of those points of a legit, when you evaluate a legit joint density function, you must have something that is greater or equal to 0, just like before for PDFs and PMFs. Okay, and before we had a single integral for probability density functions, but the integral from negative infinity to infinity of the PDF had to be equal to 1. Well, now we have a double integral, and the double integral of the joint density function must be equal to 1. Okay, so what we're going to see here is that now, instead of having curves, right, density functions you could graphically express as a curve, right? Well, now instead of curves we are going to have surfaces, and now to find probabilities, instead of using just a single integral, which would be the area underneath the probability density function, right? Instead of finding areas under a curve, right, we're going to be finding volumes under a surface. Make sense? Okay, so let's talk about an example that is going to help us have a more concrete idea of joint density functions and how we can use them to find probabilities. Okay? So, in this case, we have the following joint density function. Okay? It's going to be 1, just a constant between, for all combinations, if you will, of y1 and y2, where both y1 and y2 are restricted to be numbers between 0, 1. Okay, so since we're talking about all possible combinations of these guys, y1 and y2, a mathematician would say that we have the Cartesian product. Okay, so I'm about to show you in just a couple of minutes, in seconds actually, a graphical representation of the joint probability density function, so you have a better idea of what it looks like. Okay, and it's going to be 0 elsewhere, and we are going to be using that joint density function or joint probability density function to answer these two questions. We want the probability of these two events, the probability that y1 minus y2 is greater than 0.5, and the probability that the product between y1 and y2 is less than 0.5. Okay, so now let me show you a graphical representation of the joint probability density function. See, we have y1, this guy lives in the 0, 1 interval. We have y2 also lives in the 0, 1 interval. All pairs that you can form between y1 and y2 are possibilities. Okay, so that's why we have something that is continuous. So the surface that we have is just this. We have a constant at 1. It's a plane, right? So now I want you to go back to what you know about univariate random variables. Random variables is just, you're talking about one variable, so it's a univariate case. Okay, so anyway, if you remember, you have seen something like that in the case of just one random variable, right? We call that guy the uniform continuous random variable, right? So this is an extension of that uniform continuous random variable, but now the outcomes are not just points in an interval, are points in a region, in this case a square, and then here we have the values of the joint probability density function. Note that each of these points here are above the horizontal plane, right? And if we find the volume in the entire region, this is a box with base height, and height, and this also is 1, so its volume is 1 times 1 times 1, so clearly the volume is 1 of that box, right? Okay, so it satisfies both conditions of a legit probability, well, of a legit joint probability density function. Okay, now let's try and solve the first problem. Okay, let's find the probability that y1 minus y2 is greater than 0.5. Oh, well, we will need it later, but so we want probability that y1 minus y2 is greater than 0.5, right? Okay, so what I would do first is this. We have a lot of experience dealing with just one random variable at a time. So how about I just do something like this. Let me solve for y1. Okay, so then what we have here is y2 plus 0.5. Okay, so these two events are equivalent, right? Okay, now something that we have to do, right? We already have a graphical representation of the region, the support, we call it. So it's that 0, 1, it's the 0, 1 interval for y1, the 0, 1 interval for y2, all possible combinations. That's the entire region where the joint density function is non-zero, right? But the thing is that to find that probability that we are interested in, we have to restrict that region to the points that satisfy this, that y1 is greater than y2 plus 0.5. Okay, so now let's try and make a graph of the points that satisfy that, and then we will find the volume in that region. Make sense? Okay, so to do that, I'm going to be using R to have an idea of what we want. So first, remember that y2 is a number between 0, 1. Right? So let me create a sequence of numbers that starts at 0 and ends at 1 by and then we're going to have a difference of 0.01 between each of those numbers in that sequence. Okay? So for instance, let me show you the first few elements of that sequence we just created. Make sense? Right? Okay. But now, instead of an inequality, let me create the equality case here. y1 equals y2 plus 0.5. That's just a line, right? Let me use y1 for the vertical axis and y2 for the horizontal axis, right? So if we think about it that way, if y1 is the vertical and y2 is the horizontal, then what we have is just a line with slope 1 and y-intercept 0.5, right? So now we have an idea of what we want. So y1 is going to be y2 plus 0.5, okay? Now, as we said, we're thinking about y1 as the variable that goes on the vertical, as the y, right? That's what we usually do. That's the usual notation for the vertical axis. So y1 is going to be our y, and y2 is going to be our x, meaning the variable on the horizontal. Okay, so now let me plot. So y2 goes on the horizontal, y1 goes on the vertical. Okay, and let me use this type L. I want a line. Okay, and yeah, so let's see. So we have this. Okay, now remember that what we would like to do is restrict our attention to numbers that live between 0 and 1, right? So let me add that restriction here, right? With this, with AB line and h equals 0, I'm going to be adding a horizontal line at 0, right? And with LTY equals 2, I'm just telling R that I want a dashed line. Okay? Okay. Oh, I see what happened. Okay. Now AB line, I want a vertical at 0, right? And I want a vertical line at 1 as well. Okay. Note that is not showing exactly what I want. So let me restrict that. Let me be more specific. I want the limits for the horizontal to be 0, 1. Okay, now that's exactly what I want. So we want y1 and y2 to be between 0 and 1, right? And now let me add those horizontal and vertical lines. Okay, that's better. Okay, so as we can see, right, y1 is restricted between 0 and 1, just to remind us that. We want now, instead of a horizontal line, a vertical line here. Okay, and another vertical line, but at 1. So these dashed lines are reminding us that y2 goes from 0 to 1, y1 goes from 0 to 1, but now we want, we are interested only in this region, the points that live above that line. y1 is greater than y2 plus 0.5, and as we said, this is just a line with slope 1 and with y-intercept 0.5, right? Now note something. since we have a slope of 1, if we move 0.5 units, we're going to be 0.5 units above. So this guy here is a point with the following coordinates: y1 equals 1, y2 equals 0.5, which makes sense, right? If we had y1 equals y2 plus 0.5, if y1 was 1, right, then you would solve, and then y2 would be 0.5. Okay? Anyway, so now let me show you something that I prepared for you here to make it clearer, right? The region that we were interested in. This is the region, right? So it's what we did with R. First, we found we just created a sequence that would allow us to make this line, right? And then we bear in mind, we just reminded ourselves that we have these restrictions for y1 and y2. So this is the region that we're interested in, okay? Probability that y1 is greater than y2 plus 0.5 is just the volume of that region underneath the joint probability density function. Okay, so first what we're going to be doing here, okay, is using a geometric approach before we use double integrals, because in this case we can see this is just a box. So if I want the volume of something, and in this case the region is really nice, I can find the area of that region, and if I multiply the area of this region by the height, I get the volume, and that's it, right? So let's say that one way, in this particular case, because it's really simple, a geometric approach. So we have base times height base times height divided by 2, that's going to be the area of that triangle, times the height, right, the other height that we have, right, which is just 1, that's going to be the volume. Okay, so it's going to be 1/2 base of that triangle times height. Height is also 1/2 times 1/2, again, because it's, you know, the area of a triangle, base times height divided by 2. That gives you the area of the region of interest, but then we multiply by the height that we have from the joint probability density function, which is just a constant. It's a beautiful 1. So that's just 1/8. We already have the answer without using calc. Okay? Okay. Now let's see if we can do this using integrals. So the interesting part of doing these double integrals is being careful with the lower and upper limits that define those double integrals. Okay? So here we go. Using calc. Okay, so what we're going to be doing is finding this using double integrals. If we were dealing with a single random variable, right, we would find the integral right, using the PDF, right, the area under the density curve. Okay, now we have joint density functions, then we need double integrals. Okay, so note that y1 is restricted. y1 must be greater than y2 plus 0.5, and it goes from here, from this line, up to 1, right? So let me integrate first with respect to y1. Okay, y1 must be above y2 plus 0.5 up to 1, and the joint density function is just a beautiful 1, and I'm integrating with respect to y1 first. Okay, that's the first one. Then what we said is, hey, that line y1 equals y2 plus 0.5 is a line with slope 1, y-intercept 0.5, and since the slope is, 1, if you move 0.5 units, you have to reach 1. So this guy here is 0.5, which means that y2 goes from 0 up to 0.5, right? It's only allowed to vary from 0 to 0.5, right? Okay. So from 0 to 0.5. Right? Okay. Now, well, I'm sure that you have done something like this before in calc, right? But the thing is, you just deal with these guys, with these double integrals, one integral at a time, one variable at a time. So first, the first one, right? We want the integral of 1 with respect to y1. So that's just going to be y1 evaluated here at 1 and y2 plus 0.5, right? So let me write that down. So it's going to be just y1, and we want to evaluate this guy. Oops, not what I wanted, but let me use it. This is going to be y2 plus 0.5. This is going to be 1, and this guy here will be y1. I'm just evaluating that guy, right? And then we have to integrate with respect to y2. Right? No problem. So now let's continue. So now we want to find that integral. Zero, 0.5. This is going to be just 1 minus y2 minus 0.5, right? And we're going to be integrating with respect to y2. Let me simplify that expression. That is just going to be 0.5, right? could break down that integral into 2. Oh, there. Okay, I want an integral there. That's better. 0, 0.5. Let me copy paste this. That's what I want inside that integral. Okay, nice. And those two integrals are easy, right? So this would be just y2, right? Evaluated at 0.5 minus the evaluation at 0. So let me be lazy here. It's going to be just 0.5, right? Again, it's going to be y2, right? Evaluated at 0.5 minus 0, but we get to factor out that 0.5 here, right? So it's just going to be 0.5 times 0.5. You guys agree? Okay, next one. It's going to be just y2 square divided by 2. And we're going to be evaluating at 0.5 and then minus the evaluation at 0. So it's going to be just 0.5 squared divided by 2. You guys agree? Okay. So let me write that down. So it's going to be 0.5 squared divided by 2. So what we end up having here is just 0.5 times 0.5. That's you know, 1/2 times 1/2. That's just 1/4. .5 squared, that's 1/4 times 1/2. That's 1/8, right? But 1/4 is the same as, you know, 2/8. So let's write that down. 2 divided by 8 minus 1 divided by 8. That's going to be just a beautiful 1/8. Okay? So our approach using double integrals matches with that geometric approach. Now note, in this case we could use that geometric approach because it was just very simple. The expression of the joint density function is just you know, a constant, so it's very simple. But in other cases using that approach is not possible. Okay? Okay. Now let's do one more. Okay, that's A. Let's try and do B. Let's go back to statement of the problem. In this case, what we want is the probability that y1 times y2 is less than 0.5. Okay? So okay, let's try and do this one. Part B. So we want probability that y1 times y2 is less than 0.5. Okay, so let's try and do the same thing that we did before, right? Just let me solve for one of these guys. Now note that both of them are positive, right? So if I divide by y2, the inequality is not going to change directions. Okay, so I'm going to be dividing by y1, and then these two events will be equivalent. Okay, make sense? Okay, now let's try and again, let's try and make a graph. Okay, now remember, let's see this expression that we have here. Now we are dividing by y2, so we can't include 0. Okay, we have to be really careful with that. Okay, so now let me create a sequence just like we did before, y2, but now I'm going to start at 0.01. Okay, I'm using y2 for the horizontal just like before. Now y1 is going to be, I'm going to be doing something like this, but instead of the inequality I'm going to evaluate at the equality and see what that looks like. y1 equals 0.5 divided by y2. Okay, so y1 in this case is going to be 0.5 divided by y2. Okay, now let me plot, and again the syntax of this function plot is first you want the numbers that go on the horizontal axis and then the numbers that go on the vertical axis, type L because I want a line, and then this xlim establishes the limits for the variable that goes on the horizontal, and ylim establishes the limits for the variable that goes on the vertical. And since both y2 and y1 live between 0 and 1, that should work. Okay, so we have that curve. Okay, now let me add those dashed lines that remind us that we are restricted to that unit square. Okay, and again that AB line command using H is going to draw a horizontal line. First we want a horizontal line at 0, then we want a horizontal line at 1. We could do something similar but using V for vertical. Okay, so now let's see. What we want is the volume of that region, the points that satisfy that inequality, the y1s that are below 0.5 divided by y2. So what we want is the volume of that region, right? So now can you see that this region, well, it's not as simple as the one we had before, so a geometric approach is not going to be possible. So we have to use double integrals. Okay, now in our lecture notes I prepared a nice version of this graph of the region that we are going to be interested in. It looks like that. Okay, it's really similar to what we did, but it looks a bit nicer. And the important thing here is that I broke down the region of interest into two regions, and you'll see why that's important in a minute. So let's call this guy region 1. So note that for region 1, right, y2 is allowed to vary from 0 to 0.5. This guy is going to be 0.5, right? And it's easy to see that this point here, the coordinates of this point are going to be 0.5 and 1. Let me show you why. We know that y1 equals to 1, right? So 1 equals 0.5 divided by y2, right? So if you have 1 equals 0.5 divided by y2, you multiply on both sides by y2, you end up with 1 times y2, so y2 equals 0.5, right? So that's how we know that these are the coordinates of that point. So anyway, y2 in this region that I'm calling region 1 goes from 0 to 0.5. This one goes from 0 to 1. y1 can go from 0 to 1. So in this case, we can find the area with a geometric approach. It's just 0.5 times 1 times 1. That should be 0.5, right? Okay, anyway, the behavior of the region number 2 is different. In this case, y1 can't vary freely in that interval 0, 1. It's restricted by this. y1 must be below that curve, 0.5 divided by y2, right? And in that region, y2 goes from 0.5 to 1, right? Okay, so let's try and do this using calc, using integrals. Anyway, we don't have much of a choice. For region 1, yeah, we can find that one using a geometric approach, but for the second region, that is not going to work. We have to use calc. Okay, so let me write that down. Okay, so first one, as we said, right, if we refer to that graph we had before, we have two integrals, and I'm going to write them down both, but as I said, we already know that the the double integral on that region, the first region, is going to be just 0.5. So let me write that down. So in that case, something really nice, what we have is that y1 varies from 0 to 1, and I'm integrating that function, just 1, that's the joint PDF, and I'm integrating with respect to 1, to y1 first, and then y2 varies from 0 to 0.5. Then the next integral looks slightly, and I need the second integral, the second variable here, right? Okay. Now the second integral is going to be slightly uglier, right? Now let's go back to this. So we can see that y2 will vary from 0.5 to 1, right? But y1 must live below that curve, okay? So that's why I'm integrating with respect to y1 first, because I know that that guy is restricted. So it goes from 0 to 0.5 divided by y2. Oh, let me do it like this because I need that to be lowercase y2. Okay. And this one, y2, now this guy goes from 0.5 to 1. Okay. 0.5 to 1. Okay. Very quickly, note that the integral, we said the integral in the first region is going to be just 0.5, right? So the integral of 1 with respect to y1 is just y1. If you evaluate here at 1 minus the evaluation at 0, you end up with just 1. And then the integral of 1 with respect to y2 is just going to be y2 evaluated here, 0.5 minus 0, 0.5, right? So we were correct. But again, in that case, the region was so simple that we could use a geometric approach. In this case, it's not so simple. But anyway, it's not going to be that ugly. It's not going to be that terrible, because you just have to deal with those integrals one variable at a time, right? So the first one, it's going to be just the integral of 1 with respect to y1. That's going to be y1, right? So y1 evaluated at 0.5 divided by y2 minus 0. So what we end up with is just, 0.5 divided by y2. Right? That's the first integral. And then we have to integrate with respect to the second variable. Now we have 0.5 here. We get to factor out that constant. We know that from calc. So let me place that constant outside. Now we just need the integral of 1 over y2 with respect to y2. And that's just natural log, right, of y2. So we have 0.5 plus 0.5 times natural log of y2. And we have to evaluate here at 0.5 and at 1, right? Okay, no problem. So let's do that. So it's going to be 0.5 plus 0.5 times natural log at 1 minus natural log at 0.5. Now note that the natural log of 1 is just 0, because e to the 0 power is 1. So we already have that guy. So that's just minus natural log of 0.5. And finally, well, let's do this using R. Let's do that calculation using R. So what we want is 0.5 minus, right? Yeah. Right, because it's going to be minus times 0.5, right? So let me just write it down here. Minus this. Okay. So anyway, we were saying what we want is 0.5 minus 0.5, and now pay attention to this. If you're using R and you want to compute the natural log, just use that command, log, because the default base is E, right? So in R, in other statistics textbooks, sometimes or very often you'll see just log, and we statisticians, when we write log, what we mean is by default the natural log, not log base 10. Okay, anyway, so we want the log, the natural log of 0.5. That's it. That's our answer. So the probability of that event is roughly 84%. Okay? Okay, so let's summarize what we did in this video. What we did here is we introduced the idea, the extension of the idea of the cumulative distribution function, of the extension also of the probability density function. In one case, the CDF, in this case, in the bivariate case, it's called the joint distribution function. Instead of a PDF, when you're dealing with a bivariate distribution, then you say that you have, if you have a continuous case, right, you have a joint density function. And then what we did is we solve this example, right, that had to do with joint density function or joint probability density function. And since we had two continuous random variables at the same time to compute those probabilities, we had to use double integrals. Okay, but we can see that the ideas are basically the same as in the univariate case, as what we were doing before when we were dealing with random variables, right? But now, instead of finding areas, we're finding volumes, and that's why well, we're using double integrals instead. Okay, that's it for now. Thank you so much for watching. Please take care and keep working hard. Bye.